So this video is meant as a review of oxidation numbers. If you want to go back and see more examples, you can go back to the Gen Chem 1 lesson that's already attached. So oxidation numbers, these are the charge that an element would have if it lost an electron. And that might be keying you off and thinking, well, in ionic bonds, they do lose an electron. So we're not talking about within the ionic species losing an electron to someone else. We're talking about if you do a reaction, one of them losing an electron to someone else. That's what we're talking about. But it does follow a similar concept in many cases. And you're going to begin feeling like oxidation numbers are charges, and if you except for a few situations. Technically, and we haven't held to this strongly, when you're dealing with charge, like if it was a 3 minus, you write a charge like that, and an oxidation number is written like that. But most people don't hold to those formulations, but I'm just letting you know if you see it, that's why there's a difference between the two. So it's what it would have when it lost an electron. And there are tons and tons of reactions that actually are oxidation reduction reactions. So we need to look at the periodic chart and just review a few little concepts before we go into counting the oxidation numbers. And again, hopefully, in the majority of the cases, hopefully you'll just see that the oxidation numbers are effectively the same that you would get if you did have the charge and you were dealing with the charge. So if you'll remember the pink section of the chart right there, this section here, when it bonds with this section over here, it's an ionic bond. So it's a positive negative. Something on this side gives that a electron, making it some kind of negative, and then the positive negative, it's attracted to each other, and that's an ionic bond. So that's one type of bond, and those are the ones that the oxidation numbers are going to be the same as what their charges would be. And then we have atoms that are all within this section, like, S and O together, or just O2 by itself. Those are covalent bonds, and they don't work like ionic bonds. They are talking about electrons being shared in a bond. They are usually shared unevenly because of electronegativity. Hang on that thought. But they are usually shared in a bond. And so when you're talking about electrons in a bond actually being moved to some other species in the reaction, the question kind of comes in like, well, it's shared. So does it come from the oxygen or the sulfur? Who's it come from? So that's the tricky bit, is when we're dealing with covalence. Even if I have a sulfur and an oxygen, and yes, they both want to be a -2 charge, so they are doing not ionic bonding, but covalent, where they're sharing, even though they both want to be negative, one of them, for oxidation number purposes, losing an electron to some other species, is going to go positive. So that's the part that gets a little tricky. Also, I want to mention a quick little thing on hydrogen. Hydrogen can be a little weird sometimes. And we know that it actually belongs over here. We know that it likes to form a +1 charge. But over here, when we're talking about electronegativity, it has an electronegativity value of 2.1. Well, if you do this comparatively, fluorine has the highest electronegativity at 4. Oxygen is 3.5. Nitrogen's 3. Carbon's 2.5. And then boron's 2. So you could see that. And the rest of these, like these positively charged things, they're like 1 and 0.5 and things like that. So, and this is 3. So electronegativity increases going across and going up, and that also plays a role with all of this. But hydrogen just can sometimes be weird in compounds. So when the H is on the front, like HCl, and an acid, it's going to do its normal, kind of pretend it's an ionic bond, even though it kind of sort of is and kind of sort of isn't when it's on the front. There is a class of species that sometimes comes up in oxidation reduction, and it's only in this setting that you'll see hydrogen bonded with like one of these things, and it'll look like this, LiH. The H comes second, and when it does that, what we're saying is that it's doing an electronegative thing. And in that scenario, and that scenario only, it becomes a -1 oxidation number. It actually gets a -1 charge is what happens in those hydrate species. It acts like it's a non-metal, which it actually is. Hydrogen is just weird, y'all. So just know that in almost all cases, well, in all cases where hydrogen's in the front, it does this normal +1 charge thing. But if you see hydrogen paired up with a metal, it goes -1. All right, so that's our last, and that bonding had not been discussed previously. All right, so let's back up and let's actually see how this all applies for actual oxidation numbers. I'm just trying to clear up my chart a little bit. Oh, and don't forget also your columns. You learned all this in Gen Chem 1 also. So when you're doing ionic bonds, don't forget like the column +1, +2, Aluminum is +3, and then -3, -2, -1. This section can be -4, but it's really rare to have those acting like that. They prefer to act as covalent bonded things. These things are all some kind of a positive, ranging from like 1 to up to like 7 in some cases, and it's hard to guess what they're going to do. You just have to see what they're paired with and figure it out. All right, so oxidation numbers. This is the easy part. We're going to look at the left-hand side. If something is neutral, and I just mean an element alone, not a compound, but just an element alone, it's got an oxidation number of 0. So that's so easy. If there's no charge, it's just one element, it's 0. If it has a charge, it's just the charge. Again, that's super easy. That's what you would expect anyways. If it's an element combined with another element and it's ionic, then it just also becomes the charge. The oxidation number is the same as the charge. So this is +2, and that is -1. That's each fluorine is -1. So in all of those, it's kind of obvious, like no charge, neutral, 0. Ionic, you just, it's got a charge. You just put in what the charge is. Same for this kind of a bond. And acids, we can treat them as ionic things when the H is in front, and so that is a +1, and that's a -1. So all of those are what you would expect, even if you're doing the charges. And I just did give you the weird example of hydrides. They are kind of sort of ionic-like. And so in hydrides, that's the H written second, bonded with a metal, H is negative. So that's kind of a weird case, but it still kind of follows the idea of what's going on. This is where things are different. This is the covalent bond. For covalent bonds, the more electronegative element gets the charge it would have if it were ionic, and the other adapts. So if we look up here, we have oxygen. Remember, fluorine's the most electronegative. We have oxygen and we have phosphorus. Oxygen is definitely closer. You'd have to like take a few block steps to get over there with phosphorus. So oxygen is the most electronegative. That means that if anyone's going to be losing the electrons, it's not going to be oxygen because it has the strength to hold on to its own daggum electrons. So each oxygen is 2. There are a total of 5 of them. We don't know what the phosphorus is, but because there are 2 of them, I'm going to call that 2x. Notice that it doesn't have a charge. Over here, we do have a charge. Whatever that is, that's what it adds up to. So like in this case, it's going to add up to -3, but this doesn't have charge, so it just becomes 0. So we have 2x minus 10 equals 0. I'm going to add 10 to both sides. And that gets me 2x equals 10, which x equals 5, which means that my oxidation number for phosphorus, we always do it in terms of one of them, is +5. That should feel weird to you because you're used to saying, oh, well, it's in this column. It should be -3. But remember, we have 2 elements. Neither one of them wants to lose the electrons. This one just happens to be able to hold on to his stuff more than the phosphorus. So in the bond between them, then, or just on the element itself, the electrons are lost in a way, and it has to come from the phosphorus because it can't hold them as tightly. So we're going to do the same thing for these two. They're the same elements, so P and the oxygen, so PO4 3 minus. Each oxygen is still just the -2. That's the charge it would have, and it holds on to them. And then this has just one P, so we'll just call that X. So X minus 8 equals -3. Add 8 to both sides, and I get X equals +5. And so phosphorus in that case is, look, it still happens to be a +5. That doesn't always happen that way. Phosphorus can change. It doesn't have to have an oxidation state of 5. It's going to be very adaptive depending on what it's paired up with. So that is your review on oxidation numbers. Remember, neutral, ionic stuff is the same as charges, acids, all that. Hydrates are a little weird, but they still kind of are like ionic stuff. The only part you need to really stress about, and it's not even stressing, but is to think about, is when you're looking at covalence, again, the most electronegative gets the charge it would want to have if it were ionic. And then the other one adapts. And it adapts up to equal the charge if it's neutral or if it has a charge. That's what it adapts to.